I was strolling on the moon one day in a merry, merry month of December. Now, May, when much to my surprise, a pair of bunny eyes.
Oh, is this a neat way to travel? Isn't it great?
In the very near future, we humans will be returning to the moon, not just to visit and to do a bit of exploration, not a sort of day trip actually. We'll actually be going to the moon to set up permanent lunar outposts, habitations. And we hope to put humans on the moon and keep them there from that point forward. And of course that will mean that we will have to solve some very practical and difficult challenges. One of the most difficult being how to provide electricity on a reliable and continuous basis during the entire lunar day. Now here on planet Earth, an Earth day is 24 hours long and a night might be 12 hours long. On the moon, a lunar day is 27 days long, and so a lunar night is half of that. It's almost 14 days. Now during the lunar day, it's easy to provide electricity. You could use photovoltaic cells and maybe even thermal systems with turbines and the rest. But what do you do during the long and very cold lunar night? There are some straightforward approaches, but they tend to be a bit problematic in terms of how do you deal with the cold temperatures, and for instance, how do you deal with the very high cost. Living on the moon will be very costly. It will probably take maybe $100,000 for every kilogram sent to the moon and provided on an ongoing basis. It's very expensive to send mass to the moon from the Earth. This little video that I'm sharing with you today is a proposal to use space-based solar power in low lunar orbit to provide a way of beaming down to the lunar surface, microwave energy. Now space-based solar power is not a new idea. It was first introduced into the popular culture by a very famous American chemist and science fiction writer by the name of Dr. Isaac Asimov. Now, Dr. Asimov was actually a chemist by training, graduate of Columbia University, and it was in the 1940s he first proposed space-based solar power. Now, it's been extensively studied for use in low Earth orbit. But I think now it's time to start to look to see whether it is more directly applicable to low lunar orbit. If we can put into low lunar orbit 6 satellites, I think that based on the Selene project I'm outlining in this video, we could probably provide 60 kilowatts to 80 kilowatts on an ongoing basis, and additional electrical energy could be provided by radioisotope decay RTGs that are presently used.
And that's where the MMRTG comes in. The multi-mission radioisotope thermoelectric generator is a power source that we've used for years to power spacecraft that have gone to the outer planets, and even the Apollo missions used it on the moon. And
maybe even a bevy of batteries. But the primary thing is that if you set satellites into wisely thought out orbit, they will be in sunlight as they pass over the South Pole. Now this is the other thing. You have to be mindful that the proposal is to send humans to where the water is on the moon, and it appears that it's mostly near the South Pole. So that adds to the challenge of not only putting humans on the moon, but providing them reliable and continuous supplies of electricity. So in this video, I will explain to you the proposal for the Selene system, which is 6 satellites and providing 60 to 80 kilowatts on a continuous basis.
Watching Apollo footage of astronauts doing geology on the surface of the moon is a really great way to think about preparing for Artemis, for putting people on the lunar surface once again. We learn a lot in how they did science operations on the moon and what it's like to work on the moon. You see them doing geology. You see them taking rock samples, putting in a drive tube to take a core sample. You see them bouncing along the surface of the moon on the lunar rover that they used in Apollo 15 through 17. So it's a great way to help drive technology development for the next generation of spacesuits and geology sampling tools. In the intervening decades since Apollo, we've been training astronauts who fly to the International Space Station because when they're on the ISS, they spend time observing the Earth, looking out the window, taking pictures of what they see on the Earth's surface. Now that we're looking at putting astronauts on the surface of the moon,
the lunar South Pole holds tremendous resources that are going to allow us to continue to explore. This is a place that we've never been before. There's so much to be learned from getting boots on the ground and exploring a unique place that challenges us as humans and also helps us develop technologies that make our everyday life that much better.
So at this point, you're probably wondering, well, why not just go with MMRTGs, these radioisotope thermal generators? Well, you could, but there are several things to consider. First of all, each of them costs $100 million to produce. That's a lot of money. I can build an entire satellite for $100 million. Can you think of another thing that limits their use? Well, I gave you a clue. It's the fact they don't produce much in the way of kilowatts. And everything that had been expressed or shown in the Artemis video from NASA requires energy. Vehicles require energy, life support systems require energy, just normal logistics, keeping the lights going, keeping the heating going requires a lot of electrical energy, and it's just not economically viable to rely entirely on just one source, the RTGs, to provide electrical power for the moon. So you have to be creative, and this is where the Selene proposal comes in. You put in orbit 6 satellites. They are in a north-south orbit. They pass close over the surface in the north, but they are 3 moon radii above the South Pole when they are passing over the South Pole. And now those satellites will be almost entirely in the sun, which means that you can convert sunlight into electrical energy using photovoltaic cells on the satellites, and then just beam them, the energy down to rectenna on the ground, on the lunar surface. And then with an efficiency of about 80%, you can scale it to have 60 to 80 kilowatts of electrical power with these 6 satellites on orbit. And sure, it's going to cost a pretty penny, but the technology is readily available, and the beam steerable planar antennas on these satellites exist already. And it's just a question of doing a design build of the first one and then doing a proofing of the concept on the moon. And the rectenna can be set up by robots if you wanted to. The nice thing about the whole system is when you start to explore other regions of the moon, you can steer the beam to those other regions as well and make electricity available at other sites. You're not just tied to one site. So Selene, the concept actually is worth pursuing. And for $2 billion, you can actually produce 6 of them and have the rectenna on the moon, and you can provide all the electrical power to provide a permanent habitation. So let's look into it and let's go build it.